This one is the essential one.
No, it's okay.
So like this we can leave it. Yeah, let's just leave it like this.
I will leave this.
Okay, good.
Sorry?
We just leave it. Yeah, we'll just leave it on.
Do you need a presenter actually?
Do you have one? Like a remote controller?
Left to right and...
It's probably okay. I'll just use my... I mean, if you have one, I can use it.
Okay, everybody, I think we're ready to start. Last session of the afternoon. I'm Martin Butz and was asked to chair the session, so I gladly do that. And hope we can all catch the planes afterwards. But I think we still have 4 really nice talks. You probably saw. Actually, I got an old printout of the schedule, but could rearrange it. It's not a problem. But so we start actually with Bernhard Riecke, and let's see if it works. Doesn't matter. And yes, hopefully we have a nice session still. Thanks for sticking around.
All right. Well, thanks for still being there at the end of this very long conference. So, first of all, I'd like to thank my wonderful students and collaborators, Salvar, Sigurdarsson, and Andrew. Unfortunately, they couldn't come. Salvar moved back to Iceland, and Andrew is currently somewhere in the middle of Upper British Columbia at a meditation retreat to take a break. So, this research was done at the iSpace lab at the School of Interactive Arts and Technology at Sam Fraser University, that's close to Vancouver and beautiful British Columbia. So moving through virtual reality without moving, what I mean by that is kind of the dream we have as spatial cognition and virtual reality researchers, to be able to move you through this environment indefinitely, really huge buildings, without having to really go through all the effort of physically moving you, which can be a little bit of a financial and technical nightmare. So in particular, we asked whether using naturalistic visual cues in virtual reality might be able to compensate for the lack of physical motion and prevent some of the rather drastic errors that I'll be talking about in a moment. So here's one of the grand challenges in virtual reality and spatial cognition research, mainly that our spatial perception, cognition, and behavior in virtual reality is simply not necessarily always the same as in the real world, and that's especially true if you don't physically move. For example, people get lost more easily, or you produce qualitative errors that I'll show you in a moment. And well, this can be quite of a challenge, especially if you just spend half of your grant money to buy this wonderful new virtual reality setup, and it simply doesn't guarantee that it'll work and produce similar results as real-world stimuli. And also for research, it's an issue because, well, is our research method valid? So does it transfer? Do we find similar results, and so on? And instead of going through all the different kinds of research and prior research that half of you have co-authored and are well familiar with, I thought I'd just see whether I can actually demonstrate the main effect. So I'll show you a simple point-to-origin task similar to what people see in our experiments. You'll see a visually simulated translation, rotation, another translation. At the end of it, I ask you to point back to the origin of locomotion as if you would have physically moved yourself. So let's try this out. So please, try to stay awake for 15 seconds. So here's the simple optic flow stimulus. As you see, there's no landmarks, the translation, rotation, another translation. And at the end of this, I'll ask you to point back where you started from. You. All right, keep your hands out there. Okay, if you look around now, what you notice is, oh, thanks for replicating the literature. What you notice is that even though we're supposed to be kind of the spatial cognition elite of those who haven't left already, but still we can't agree on that. So some people point into like left backwards, right backwards. How is that possible? I mean, we all have a degree in all of this. So here's an attempt of an illustration. So here's a top-down view to demonstrate the two typical strategies we observe. So this is, well, you can only see half of it. Sorry, projector is a bit bad. So people, if they physically move, they point back to the origin of locomotion. I'll illustrate you because the slide doesn't work. So even if eyes blindfolded, people normally would point back there. However, we also observe people who point in this direction. You don't observe this when people physically walk, but for imagined walking or for optic flow stimulation, you observe this, sometimes called a Nonturner behavior. So you might wonder, well, what's really going on here? How does that make sense? And in a way, it does make sense if you think about what might be going on in the thinking of the non-turners, the so-called. Oh, there's supposed to be a bubble here. Okay, so it seems like they act as if they would not update the perceived heading during the outbound path. They're well aware of the layout of the task, the trajectory, but they point later on to the right side because they act as if they would not have updated their heading. And probably about 1/3 to half of you did this, which is kind of the standard thing you observe for these kind of tasks. And in a way it makes sense, given that strategy, so here's a kind of PowerPoint illustration, that indeed you do point rightwards if you point as if you're still facing the original orientation. And this is one of the reasons why we call these folks non-turners, because they act as if they would not incorporate the turn into their representation which they use to point. And we observe similar results for just purely imagined locomotion. If you use optic flow displays like you've seen before, typically about half of the people, sometimes even more, show this kind of behavior. It never occurs though when you physically move. So one of the possible solutions would be to, well, simply physically rotate the people during the visually simulated rotation. And that's indeed what we did in another study that I might briefly touch upon here, where we used a little rotational simulator. So whenever there was a visual rotation, people actually physically rotated. But as mentioned earlier, this doesn't fit into every office and budget. So another solution to try and circumvent the problems of these non-Turner behavior, which you don't really want to have, you want to transfer the results, might be to go beyond the classic optic flow stimuli. Here's like a star field stimulus where you can indeed perceive the heading change, but you might argue that it might not be the most ecologically valid paradigm, similar with tunnel paradigms and so on. So what would happen if you just, instead of using this, take a more natural environment where you can feel spatially present in? And indeed, some of our earlier research showed that if you use such a naturalistic, landmark-rich, immersive virtual reality, this can be sufficient for supporting obligatory and automatic spatial updating of rotations. What that means is, if you're in immersive VR setup and you know this, it's a Tübingen marketplace here, you know this environment, you see in your view, it's not just the view, the whole environment is kind of automatically and obligatorily re-anchored in your brain. As soon as you have your eyes open, this basically switches your mental representation. Quite a strong effect. But there, this was just done for rotations, not for translations. So one of our research questions was, well, can naturalistic visual cues in virtual reality prevent these kind of categorical errors and non-Turner behavior that we observe by affording automatic and obligatory spatial updating, even for these kind of slightly more complex curvilinear paths? So to study this, we put our participants on our simulator. They had a head-mounted display on, was head-tracked, a pointer, and this kind of the stimulus they saw. They were passively translated around different streets, fairly naturalistic looking. You could look around, there was head tracking going on, but they were passively transported. And at the end of the trial, they were asked to point back to where they came from. And as you notice, although it looks naturalistic, nothing in the final view indicates where you should point to. So people still had to somehow integrate over the rotations. And, well, so this is a top-down view, use different angles, quite extreme variety of angles indeed. And in the current experiment, the one I present here mainly, we just used visual-only turns. In another experiment that I presented a few months ago, we also compared them with real rotations. So, does it work? What did you find? First of all, this is just a snapshot of the initial views for the different rotations. But the point is you can't really see how far the path is rotating, so you cannot really do advanced planning. Here's a typical Bernhard plot, top-down view. What you cannot really see well is there's different paths here, and so this guy is at the end of the path, and each of these individual colored bars with a circular mean pointing direction for that participant. So one bar is one participant, and if they it's a longer bar, so they're closer to this unity circle, that means they point more consistently. So there's a way to simply collapse all the data into one slightly crazy plot. And what you see here is that there's a large between subject variability in the data overall, which is what you typically find unless you train that away. And overall, 20 of our 24 participants clearly pointed into the qualitatively correct hemisphere. That's lower, that's a higher percentage of turners than you would observe for optic flow. So something about these naturalistic stimuli is actually working. So that's good. There's also one strange participant here that somehow just kind of points back. That's something we, even though the task is very clearly described, and they can do the same thing when they physically walk. We actually observed this in another experiment as well, and I presented more on that at the other Spatial Cognition conference in Bavaria just a week ago. If you look at the more quantitative data, so you plot the pointing area, you see for small turns, people overestimate the amount they turn, and for larger simulated turns, they underestimate it. So overall, you end up with some kind of regression towards mean responses, but still people are far from chance. Now, in this experiment, we also observed 3 participants that showed non-turner behavior. Here they are. So the gray arrow here is the prediction for non-turners. This is the prediction for turners. And as you can see, they're really very close to the prediction here. And if you plot again the pointing error, non-turner prediction, turner prediction, highlight this here, they are perfectly on track. So in a way, they operate perfectly, but just have the wrong strategy, because that's just not what we asked them to do. But they're incredibly consistent, and it also suggests that they can update the turning angles pretty well. Kind of what they do is more like this, so they don't update the heading. That's what you can't see on the slide because of the projector. Another research question we had was about the processing time needed by turners versus non-turners. And why? Because we had 2 different predictions. So if people would need to use effortful processing to do the task similar to mental rotation, then you'd also expect the response time to increase with the turning angle, similar to the classic mental rotation task, Shepard-Nessler, and so on. And they should be overall a bit slower. However, if the stimuli would be sufficient to enable automatic spatial updating, online updating of where they need to point to during the excursion trip, then they should be a bit faster, and they shouldn't really need any costs in larger angles, so the response time should not increase with turning angle. And in the data which was presented in Bavaria, we found indeed this distinction that the turners operated basically on automatic spatial updating, while the non-turners, it seems like they took overall quite a bit longer, and there was also an increase with turning angle. So it seems like they might use more effortful, cognitive, demanding processing. So what did we find here? So that's a used optic flow. Here we use naturalistic hues. And first of all, well, we find only about 12% of the non-turners here. And if you look at the data, there's virtually no difference in the response times. There's a bit of variability, but nothing consistent. And response times are overall fast, and there's no increase, so this kind of argues for automatic spatial updating. But you kind of wonder, because you still observe this non-turner behavior. So how does that make sense? Well, it seems like even the non-turners did more or less automatically update something, definitely the path layout, also where they had to point to, but they didn't incorporate the heading change. So it seems like the visual cues we used, at least for the non-tourists, was not sufficient to obligatorily induce an automatic obligatory updating of the heading change. So we're not quite there where we wanted to be. But it's interesting. Well, I think it's interesting. Well, still you might wonder, well, who cares about this? And well, I think from a pure research point of view, this is quite interesting that we, even for the simplest possible non-trivial spatial cognition task, you find different strategies. People cannot really do these super simple tasks just giving optic flow, even though all the information is in the optic flow. In principle, they should be able to do this, but they're not. This tells us a lot about the integration, also the integration of different reference frames. You have the kind of embodied reference frame where you physically are, from which you point, and then the virtual reference frame. It seems like when there's a conflict, people have a particular issue with updating that. And all this basic research can really help us to improve the human-computer interfaces, so we can try and apply and integrate these findings. Also, we have like a very simple test now to basically check your virtual reality setup, how effective it is. Does it enable, does it trigger obligatory spatial updating? And even such a simple task can be used to investigate that, improve the technology. And the better setups we have, the more we can actually use these to improve our research and do things we could not have done before. Thanks. This is my last slide. So in conclusion, I'd like to basically summarize the things that so I hope to have convinced you that these strange non-Turner data actually do exist. About a third or so of you exhibited it yourselves in the little demonstration. Here we had only 3 persons as non-Turner, so something about the naturalistic cues was working, but we have very clear evidence that, well, some people still don't update their cognitive or perceived heading, which is an issue, especially for real-world transferability, but also interesting from the spatial cognition point of view. So the visual cues we used, despite being naturalistic, did not really obligatorily trigger spatial updating of the heading for all participants. Well, that could surprise us a little bit, given the previous finding that such naturalistic cues should really do the trick. So where could that come from? Well, in the previous study we just used rotations. Here we also have a translation component. So could that be part of it? But probably not. If you look at the literature, all the other optic flow studies or imagined locomotion, it's always the rotation that people have an issue with, never the translational part. So it seems like that's probably not the case. Another difference is that in the current study, from the final view, you didn't have any landmarks, anything you could use to reorient. There was nothing indicative of where you had to point to. Whereas in the other study, people were familiar with the environment, so that could trigger the whole representation beyond what you currently saw. And we believe that this is probably one of the main differences that why we still observe non-Turners in the current study. And, well, I mentioned before that we also ran a study where we used physical rotations because basically a lot of previous studies, like Trotsky had a seminal study where they showed that if you physically rotate, people automatically and obligatorily update their cognitive and perceived heading. So if that was your case, if you physically rotate people, then you should get rid of all the non-Turners, because everybody would have an automatically updated mental representation. They should do the task well. So we used our circular treadmill there. A surprising result is we still observe the same people that still point in the wrong direction. So it's not quite there yet, but it's interesting because so something still doesn't seem to be perfect. We're almost there, so more than almost 90% show the behavior we're interested in. So in conclusion, I think we have a nice simple experimental paradigm that lots of people, increasingly amount of people use, that we can use to assess the effectiveness not only of our spatial cognition but also of the virtual reality setup. So in concluding, I'd like to thank all the various funding agencies, and as usual you can find more information and some of the videos and more on our website at iSpacelab.com. All right, thanks.
Super, thanks. There's time for questions.
I came late, I'm sorry. I didn't. Were they doing only curvilinear turns, or were they? Did you have a condition where they just turn by an angle without seeing this long curve?
In this experiment, we only had curvilinear paths. Basically, whatever you would do with streets, In the early experiment, we also did like you walk, you turn, and then you continue. But here, because we wanted to stay in the motion metaphor and use a continuous rotation velocity, there was only curvilinear paths.
That might explain your percentage of, quite low percentage of non-turners, because it's very hard to evaluate the turning angle, because the optic flow shows only a little portion of it doesn't allow for a configurable information.
It's a good point. Other studies from Klaus Graumann and myself also show that even if you use a curvilinear path with optic flow, you still find the same amount of non-turners. So it really seems to be in the visual stimuli here that the naturalism somehow helps to automatically update this, but not for everyone.
What if you used like a forest, so that instead of having structures like the building that has a certain direction of curvature that you can see, you just have structure that's in the environment? Because I don't know what other optic flows have been used. The one you showed us was a ground plane.
Yeah.
There's no structure. What's your intuition? Would a forest accomplish the same thing, where there's no physical structure to give you the curvature, but there's still more information about things?
So we haven't tried that yet. It seems like it's not the amount of optic flow, it's something about the naturalism. Like in a current study that Salvar's trying to write up as a thesis, we compared the optic flow with the naturalism and had an in-between condition where we just used the ground plane, but had a tiny little indication of where the road was going just for the next few meters, and that alone already helped people quite a bit. So it's like you don't even need the trees.
Yeah, but the trees might be less than that.
The trees might be less if you cannot use them to anticipate which direction you're turning.
Which direction you're going to turn,
yes.
Yeah.
So even just seeing which direction you're turning
Seeing
seems to help
curvature in the
a little bit.
environment, yeah. It'd be great if you could. Thank you.
There's another question back there. Yes?
I'm interested. Are people consistently non-turners and then turners? So you're a non-turner. Are you a non-turner in your sort of environment you're in? Or is it that you've said, okay, overall they're non-turners, but actually sometimes they did get it right?
Yeah.
How does that work?
Good question. I should have paid you for asking this, because that's exactly what we're currently doing in another study, looking for people whether they switch and use different strategies. So in this study, people were fairly consistent. For other studies, sometimes people switch back and forth. They definitely switch depending on the stimuli. So if you have more compelling stimuli, more naturalistic, there's less. If like for one experimental paradigm, you probably will end up being a turner, and for the other one, you will be end up being a non-turner. You might also switch, especially if people are really unsure about it. You can very easily train that away, though. But we decided not to do this because we find it interesting that people do that.
One more question?
Excuse me if I didn't understand well. So you did an experiment with only optic flows,
Yes.
and an experiment with both optic flows and rotation, so they could feel that
Yes.
they were rotated. What would happen if they had only rotation, so you blindfold them, put them on a wheelchair around? Do you think that would like suppress the non-turners because they have only like rotation?
You just got a little wheelchair to try this. So in the previous study by Klatsky, if you people were just physically rotated, and that got rid of all the non-turners. However, in our experiment, they were physically rotated. That didn't do the trick, so it's not quite clear what exactly it is. So that's why we're researching it. Excellent question.
Okay.
All right. Thanks.
Thank you very much. I have actually one last question for you. So which direction should we have turned? Should we have pointed to?
I think it was a right rotation, so you should have pointed. So who pointed? You'll get your prize afterwards.
So this was no.
So if for a right turn, you normally should turn to point to the right. But that's not what we ask people to do.
Alright, so let's not think about what we did. Okay. Okay, we've got it all set up. Wonderful. Next turn by